Good afternoon, everybody. So I think I've just done my trick to make you laugh already. So mission completed. Right. I'm waiting for my slide to come up. Right. Posco, so from Loughborough University. So I'm academic, and I also realize I'm in your way to the best part today. So I will try to make it really quick. Depends on how many tens that I've got. Sure. All right, sure. Then I'll do slowly then, because that's what I'm really good at actually. So sure. This is I'm not certain whether you are interested in congestion control. This is a piece of work that we've done together with two Chinese universities, one in Macau, one in Guangzhou. Now here we go. This is about myself. So if you complain about the accent or English not being good, so excuse me. So I grew up and then I was educated in Hong Kong. So and I only took up my job in the after I've done my PhD in Hong Kong. But myself, I'm more like a what we call a system person. So I like building things, breaking things, and so Tim Chong here, so he knows me, and then he knows one of my projects in building Raspberry Pi cloud, so which involved like putting together hundreds of Raspberry Pis, and then we try to look into miniature cloud and things. But anyway, so today we have nothing to do with, my talk has nothing to do with these. So one thing that I find interesting here, so throughout today's discussion with people and the question that I received, among other questions like, where's Loughborough? So I was right to put a slide in here actually. So we are, so I can see better from these sides. So Loughborough is here, so we deliberately put a bigger text here so you can see it. Leicester's here, well, actually Nottingham is somewhere here. So it's in between Leicester and Nottingham, so north of London. So this morning it took me an hour and 15 minutes to come to London first, and another 30 minutes-ish to come from St. Pancras. Like, four tube stops, like 30 minutes. Anyway, so sure. However, Loughborough University itself is more, we call it research-intensive university. So we do research in this university. Right. So internet itself is pretty much as old as myself. So I'm giving away my age now. So if you know how old is internet, so that's pretty much how old I am. Right. We, as network engineers, I see myself as one of the engineers as well. So we spend a lot of time to make internet better, faster. But then the truth is, there are still a lot of congestion in the internet, in the network. And congestion itself causes problems because it introduces latencies. Right. Once you have congestion, then your queue start to build up. Then there will be packet drops, and then you have timeout, retransmission mechanisms. Everything can kick in. So I'm not sure these numbers make sense to yourself. We took it from paper, so we believe they're true. Latency itself, in turn, will have some certain contribution to revenue, or at least to the customer experience. In the research community, almost every now and then, we see a new transport control protocol with new congestion control mechanisms, hoping to solve the problem, so to eliminate congestion from the network. The question is, how successful we are. So can one congestion control rule them all, or is there any congestion control that can solve every problem that we have. So in order to find, to look into these, so we set up a small test bed that we try to find the answer. So then we have a web server. We set up a web server in a private data center in Guangzhou. Basically, it's a campus data center. And then we, again, set up 2 clients. This is with one of the clouds in Beijing, and then this is with another public cloud in New York. Then we try to do a small file transfer, like file of 50 megabyte of size. And this is what we found. So what are these? Basically, so qubit, Reno, BBR, Hybla, Illinois, Vegas. So these are default, well, rather than saying default, so these are the congestion control that you can find in today's Linux kernel. By default Linux kernel, we use qubit and Reno. So from this figure, what we want to say here is, so basically, prime backend, basically, there's the this unit here. So what it means here, you see the bars goes up and down, and then this is about the average throughput measured in terms of megabit per second. So different congestion control algorithms, they will have very different performance. And so the reason for this, we look further into it. Basically, then every congestion control, they have something we call it, okay, they are designed to suit specific needs. For example, in here, so qubit Reno, they are more like loss-based congestion control. They are more sensitive to loss signal, packet loss signals, in a sense. So throughout this experiment, we see sometimes these, for this one, say for example, qubit will have better performance. For this case, Reno will have better performance. And then in the end, when we look into the run trip time, and then we notice the run trip time, well, actually, this is not a truth, but we can close our eyes and then tell. So the run trip time can definitely go up and down over time. And then, in fact, these, on the other hand, has very substantial impact on which congestion control that you use. So then, from here, simply we can tell, okay, given a one congestion control algorithm here, it's difficult to tell which one can perform best at which time, right? Because at different times, they can do better than the others. So now the question is like, do we have to choose just one of them? What if I want to use all of them? So, because they are already available in the kernel already, we can use any one of them. However, existing mechanism does not allow us to manually configure and change to the most suitable congestion control that we want to use. The reality is, if you want to use very specific one, you have to go and then configure these yourself. And then, which is very difficult because think about in cloud environment, if your data center is a multi-tenant data center, and then definitely you wouldn't want to go into the stacks and then configure these for the tenants because you will never know what are being run inside the virtual machine from these tenants. Even for a single tenant, even they say, okay, I would like to manage these myself, then normally these tenants, they will have a few different services running on top of different version of operating system for the sake of either like, fault tolerance or security, or just for the sake of load balancing. So it's really difficult to achieve this. But then we say, okay, even there's an option for you to say, okay, you can configure your congestion control. So Linux kernel allows you to configure congestion control as on per socket basis. For one socket that you create, you may want to use Reno. For the other socket that you create, you may want to use qubit. However, as we notice here, so even for a connection maybe over a single socket, when run-trip time varies over time, it also means that the congestion control that you choose for that specific socket might not be the best choice again. So what do? So basically, so we want to have a tool that would help you to choose the most suitable congestion control on the server, or like for multiple servers. So to do that, then we try to look into these. So first of all, it has to be transparent. So, and it shouldn't get in the way between the traditional TCP end-to-end services. So it shouldn't require you to go into your server to manually to change and then configure congestion control for the servers. And as opposed to per socket level configuration, we want to give you a per flow level granularity. So you can decide for this flow what congestion control that you would like to apply to it. So the granularity is high. And it has to be able to adapt. In a sense, it means it should be able to choose the best one for you. So the simple idea here is, so instead of coming up with yet another congestion control, and then we say, okay, our congestion control can rule them all, and then we know that's not possible. So instead of saying that, we give you a choice, say, now, this is a tool that you can use. With these tools, then we'll be able to switch in between different congestion control as network dynamic changes. Right, so this is more like our design and implementation objective. So in order to achieve transparency, then we choose, mind you those, because at the moment we target like a cloud environment, for example. So we've decided we should implement this mechanism onto Open vSwitch, because we know Open vSwitch as a fact, it's default option for many hypervisors in the cloud environment. Right. So just quickly, so if you're aware of these names, so these are some similar work published in other paper, and then we try to compare Mystique, the tool that we have come up with these other tools. So simply what we want to claim here is like we'll be able, with Mystique, we'll be able to achieve dynamic congestion control switching, and you need not to modify your existing TCP stack on the server. And then we'll be able to support per flow level congestion control. Right, so then exactly how we did it. Right, so this is the overall view of the Mystique that we have implemented. So packet in means no matter client or server, so you will have packet coming in to the Mystique. So in a sense, Mystique will sit in between client and servers. So to some extent, you may say, okay, it's a bit intrusive, but yes, we need to be a bit intrusive in order to be able to keep track of every packet stage, the stage of every single flow. But by doing that, we do not require you yourself to modify the kernel itself. So when packet comes in to the state module, so if it is packet from the server, then we'll monitor this congestion window. If the packet are from clients, then we'll keep track of acknowledgement, the sequence number in the acknowledgement packet or other packets. So then once the state has been kept track of and then been updated, and then we'll be able to determine which congestion control that is most suitable for this flow, we call it. And then once this is determined, basically, so the only thing that we need is the congestion window size. So we compute the congestion window size and then use the enforcement module to enforce the server to follow our decision. So now, more specifically, so I'm going to just skip this one because briefly I explained that already. So Mystique provides some things to help you if you want to implement your own CC schemes. So more specifically, this is a slide that I want to move on to. TCP use congestion window and then receiver window to control the flow of the packet being dumped to the network. So it basically determined how much data to be dumped to the network by taking the minimum value of congestion window and the receiver window. Now, what we do basically, we specifically keep the web server. If we have a web server, and then we ask web server to basically keep their congestion window really high, meaning web server will actually dump the packet at a very high rate to the network. And then we'll stop any congestion signal going to the web server. So once congestion is detected, the congestion signal will stop from inside Mystique. Mystique will use this congestion signal if it's lost or if it's packet like long RTT, then we will determine which congestion control is best. Then the trick that we've done here, so this is a trick that we applied. We compute congestion window from within Mystique, and then we replace the the receiver window going to server's TCP with our congestion window. So we replace from within web server itself. Web server has congestion window and receiver window. We compute a new value for the receiver window. We keep this one really high. All right, we keep this one really high. So basically, that's how we trick the web server to keep pumping a lot of data to the network. Then Mystique will pace the sending rate for the web server. Right. So just quickly, one example that we have here. This is the example that we implemented. So it doesn't mean you have to follow this one, but then this is from the experiment that we did at the very beginning, the graph that we showed you at the very beginning. So this is the decision that we made for further experiment that we can we did. So if there's no loss, and then by default we'll choose Hybla as the default congestion control because it's loss-based congestion control. So when there's low loss, Hybla will perform best. This is from our observation. If the run-through time is smaller than 50 milliseconds, then the init noise should be used. For all other cases, we use BBR. So these, if you ask me why these are the choices, that's based on our measurement studies. All right. So your scenario may be different from this one, but then this is from our measurement study that we did at the beginning of this project. Right. So now we clear that. So what Mystique is, and then the trick that you can use to play with Mystique. So then we have some suggestions about how or where you can deploy Mystique in the network. You can set up a box and then run Mystique in it. So basically Mystique itself as a server, but then it will allow you to set up a new server, release old one dynamically, because Mystique will be able to keep track of the TCP states. However, this means the switch will need to redirect the traffic between Mystique virtual machines and then the actual web servers. Well, our more preferred option will be in the hypervisors. So if you deploy Mystique within the hypervisors, then it itself will be able to serve the web servers running as virtual machines on top. And then you'll be able to switch and then forward the traffic for the web servers. And then, of course, you can also employ Mystique in routers and switches. This could be potentially a really good location to deploy Mystique, but then the trouble is when the traffic intensity is really high, then the overhead incurred by Mystique may be a little bit higher in this case. We haven't tested that in production environment because, like, simply in the university we don't have production environment. But then we performed some analysis based on small-scale testbed. So this is how we implement it, and then we are currently cleaning up the source code, and then we will publish the source code again on GitHub as well. Right, so I've introduced what Mystique is and then how it can be set up. Now, just quickly on how we evaluate Mystique. As I said, we don't have production environment, so we couldn't offer you how it works in actual production data center. But then we have a small setup here, and then we use virtual machines in the cloud environment as well. So we use two clouds for this purpose. We have a private cloud, which is the same that we used for the study at the very beginning, which is a data center in a university in Guangzhou, China. And then we have another, we use another cloud in Singapore. And then we also set up 5 clients at different places, including London, UK, and then US. So these are all inside either private cloud or public cloud. So this is how we set up. So Mystique in a VM. So we look into these 2 environments. But then in the following, I'm going to report the results. They are mostly coming from here. And we have published a paper about this work, and which has the same name as this talk, and then we have a lot more results in the paper. But then due to time constraint, but I didn't know I have an hour to talk about it, so I didn't include everything here. So in the following, primarily we'll focus on Mystique in hypervisor. Right, so we measure transfer completion time and throughput, as well as loading time. For more specifically, for these 2 experiments, we use both large file and a small file. Oh, I think I should have swapped these 2. So yeah, proofreading. And then we try to look into loading time of websites because we know, in real production environment, more likely you run web-related services on top. And then we looked into 5 popular websites. So you may want to dispute this one, but this was the name appeared in another paper. So then, in order to compare these against our other work, then we choose the same one. So yes, then we compared Mystique against these congestion control that you can find inside Linux kernel. Right, so bear in mind, by using Mystique, there will be one more hop to one web server because Mystique will sit in between client and the server, in that sense. So basically, then we employed everything one. So what does it mean by everything one? So basically, this is one. So we start by monitoring the connection. If we do not detect loss, then by default we use Hybrid. If loss is detected, but the runtime time is more than 50 milliseconds, we use Illinois, or otherwise we use BBR. So for just quick comparison, small file and large file in private cloud. So if we look at here, so this color means different congestion control protocol. So Mystique is in red, and in most cases it performs average transmission time. Most of the time it performs best, and then more specifically, so if you compare it with default qubit here, so it can perform really well. It can improve performance a lot over qubit here. And then similarly for the large file here, so the red bars means Mystique. So constantly then we have the best performance. Now we also look into, as we said, the by comparing the websites. So how we did that actually? So we didn't pull the traffic from the actual website themselves. So we clone their websites and then put it in one of our cloud testing environments. So in that case, we make sure the condition is consistent. So it's basically counting, loading the number of objects and things. Right, so well, basically, and then as you can expect, then what we want to say here, so the red bar is the shortest in here, meaning so we have the smallest loading time, so you can fetch your website in the shortest period of time in comparison with all other congestion control protocol. So Mystique on router and switch. In this case, we look into throughput, and in this case, instead of we demonstrating you red bar is the shortest, and then we try to show that red bar can achieve the highest point in a sense. Right, so basically we quickly looked into Mystique's performance. So again, a lot of data is available in our paper. So one thing that we also want to emphasize here, that's the overhead. Remember I said, so if you want to deploy Mystique on router or switches, and there is a concern about the overhead that you can add on top, because if you say, for example, 1 gigabit, well, switch probably it's fine, but then if let's if a switch that has 10 gig or even higher interfaces, so running at full line rate, then the even 2% overhead could be quite significant. But anyhow, so we want to demonstrate by using Mystique, you do get this additional overhead because we will need to keep track of all congestion control states in memory. So Mystique calculate RTT, minimum RTT, and they keep track of current bandwidth, maximum bandwidth as I've seen before. It keep track of congestion window size. So all these will consume like CPU time and the memory. So it does comes with a cost. But then our point basically is it's worth paying, right? Given the benefit that you can get from using it. Right, so these conclusions are not important, but then I think I want to emphasize the reason why I'm here, because I would like to hear from you, because quite often we, as academics, we give away impression we normally hide behind our doors in the office doing something nobody would use. So I would like to hear the comments from the community, and I would like to improve the work that we've done, and then hopefully this can be something that's really useful to everybody. So thank you. That's everything from me.
Thank you. Thank you. Do we have any questions? Do we have a mic for Tim? Oh.
Thomas Morales from LMAX. I think one of the network devices that I was missing on your presentation is the load balancers. Because at the end of the day, most of the services are behind a load balancer. So how you test Mystique inside the load balancer?
No.
What's plans for do that?
Well, we don't. Well, if load balancer terminates from the TCP connection there, then we wouldn't be able to work with load balancer. So it depends on what type of, because sometimes some load balancers use net. So if it's net-based load balancer, then the TCP connection will be terminated at that point. So then we wouldn't be able to keep track any further.
Yeah, but at the end of the day, you have two TCP connections, one with the external user and then another one with the backend.
Yeah, so then we wouldn't be able to talk to the, because remember what I said here, so we enforce our trick by overwriting congestion window from the web servers. So if it is behind net, we wouldn't be able to tell which server is which.
Yeah. Well, thank you.
Thank you.
Okay, Tim. Could we have that mic up a bit, please?
So to what extent do you think in typical deployments there's systems that generally speaking to servers at a wide variety of conditions in terms of high RTTs or loss? Do you think generally systems are either deployed in the data center with very low latency between them, or with so many CDNs out there, typically you don't see the high RTTs?
Right.
I think the real benefit is in being adaptive. Right.
So I think the real benefit being adaptive is, well, basically, as I said at the very beginning, so there's no single congestion control that we can say that's best for every scenario. Because when condition changes, then maybe there's one better than the other. And then, say, even within data center environment, so we are more looking at, say, a web service that you might talk to client from outside the data center in that scenario. So when you talk to, say, for example, if you serve even maybe just London and Loughborough, and then the RTT can change over time in single connection, and then, well, basically network connection that changes over time. We know that because we perform measurement and things. So I guess the general answer to your question, I think we don't, well, although we say we target the data center environment, I don't think there's significant differences as far as Mystique is concerned, because we'll be able to choose whether you are experiencing high loss or whether you are experiencing high RTT. So basically then we choose one best suitable for you.
And with one down the front. Just no. Any more questions? Sure. Thank you very much, Doctor.
Thank you.
Yeah.